Alright, thanks for watching. And today I want to do something really cool and very exotic. So on this other math channel, so TBs or TIBs, I don't know how to pronounce it, but anyway, it's a really cool math channel. And on that channel, TBs showed that what like a math exam from the 1850s looks like. And that gave me an idea. I was like, well, since I went to a French school and took a French math exam, today I want to show you what like a French final math exam looks like. Because everyone in a French school at the end of 12th grade, they have to take this baccalaureat, which is like this big exam that's pretty traumatizing. And to be honest, even to this day, I wake up at night being like, I'm taking the bac, but still, it's a really cool thing, and I kind of also want to show you the difference between, for example, American culture and French culture, especially in the way they learn math. And by the way, the cool thing is, for this French exam, there are many different subject practice tests available, because basically not only for every French department there's an exam, but also for different countries. Like in the US, there's a French math exam, or in Pondichéry, there's also a French math exam, or in Polynesia, there's an exam. Or this one I took from Lebanon, okay, from 2018. And this is one sample question from it. So usually you have like 4 or 5 exercises with a bunch of subparts. So this one is based on calculus. So consider the following family of functions. So let fn of x be ln of x over x to the n. And consider this on the interval 1, 5. And those functions are a family of functions. In the exam, it gives you sort of what their graphs look like. So notice in particular at x equals 1, fn of x is 0. So all those functions start out at 0, and then they just increase like that. Maybe like this, something like that. Whatever they look like. So it's from 1 to 5, and each function fn has a certain curve, Cn, a graph Cn. Okay, but that's not the question, so a bunch of questions. First of all, let's calculate the derivative of fn of x with respect to x. So the first question is show that the derivative of fn with respect to x is 1 minus n ln of x over x to the n plus 1. So, and by the way, what I really like about those French exams is that it's not like in America where they give you one problem and then you move on to a completely different problem and the problems are not connected. French exams, they kind of tell you a story. We want to start with this question, and then question 2 depends on question 1. Question 3 kind of relates to questions 1 and 2, which sucks if you don't know how to answer question 1. But if you know how to answer it, it's beautiful. It's, as I said, like a math story. So let's calculate this. So the derivative of this, and for this we want to use the Q-Chen loop. So the quotient rule. So the derivative of this is ln of x to the x to the n prime. And this is, again, the derivative of ln of x, so 1 over x times x to the n, minus ln of x times the derivative of this, and x to the n minus 1, over this squared, so x to the n squared, which becomes, so x to the n minus 1 minus ln of x times n x to the n minus 1 over x to the 2n. And the whole point is not just to find a derivative, but also kind of simplify this, because notice both terms involve x to the n minus 1. So x to the n minus 1 times 1 minus n ln of x over x to the 2n. And then this, how does it simplify? That's x to the n minus 1 minus 2n and that's x to the minus n minus 1, which is precisely 1 over x to the n plus 1. So this in the end simplifies to 1 minus n ln of x over x to the n plus 1. So indeed, point for me, the derivative of fn of x is equal to this. And then let's move on with the next part of the story. So we know by the extreme value theorem that those curves, they have maxima. So like Cn has a maximum at this point. Let's see, it looks like this. Cn plus 1, sorry, it's like C1 has a maximum here, C2 has a maximum here, C3 has a maximum here, etc., etc. And let's call An the y-coordinate of that maximum. So this would be A1, this would be A2, this would be A3, A4, etc., etc. And it turns out those maxima, they have a very nice property. So the y-intercepts, they actually lie on a very nice curve. So let's say the second part. So let An be the y-coordinate of maximum of Fn on the curve Cn. Show that An itself lies on a graph where gamma is the graph of y equals ln of x over e. So it's neat. Not only those curves are ln of x over x to the n, but also the maxima are on those curves. So not the maxima, but the y-coordinates of the maxima. And how do we show this? Well, as I said, in French exams, the questions are interconnected. So let's use the fact that the derivative equals to 1 minus ln of x over x to the n minus 1. So let's use the usual calculus trick of finding the critical points. So find the points where the derivative equals 0. So fn prime of x equals 0 if and only if 1 minus n ln of x over x to the n equals 0. And by the way, it's important that we're on the interval 1 comma 5, because technically you have to find the points where the derivative doesn't exist. But here on 1 comma 5, we're not dividing by 0. So on 1 comma 5. So in other words, we can literally multiply by x to the n, and that's the same thing as 1 minus n ln of x equals 0. That's the same thing as saying n ln of x equals 1, and then ln of x equals 1 to the n. So x equals e to the 1 over n. So a candidate for the maximum would be the point e to the, so a candidate for the x coordinate of the maximum would be e to the 1 over n, but we just have to justify that it's a maximum. So, and this is also very important. So usually in American system, well, they say show your work, but just to check that you didn't cheat. But in the French school system, it's very important to kind of justify your answer. So you're not only graded on the correct answer, but also on the way you write your answer. So you do have to justify why this is a maximum. And the cool thing is, here you don't really have to check the endpoints, because you don't really know the value at the endpoints. But we do have this nice thing. Notice this part, if x is less than e to the 1 over n, then you can actually do the same thing, and you get that 1 minus n ln of x is actually, I think, positive. And this is the same thing as saying fn prime of x is positive, which tells you fn of x is increasing on 1 comma e to the 1 over n. So actually each function here, it's increasing here, and similar you can show if x is greater than e to the 1 over n, this is decreasing. So let me just double check. I think that's true. Okay. And therefore, what do you have? For each function, it's strictly increasing here, and it's strictly decreasing here. And I think in America, they call it like the first derivative test for absolute extreme values. If you have a function that's increasing and then decreasing, this point is indeed a maximum. So here, that's not a problem. So we found the coordinate, the x-coordinate of the maximum. How do you find the y-coordinates? Well, use the fact that fn of x, it's ln of x over x to the n. It's ln of x over x to the n. So fn of e to the 1 over n, that's ln of e to the 1 over n over e to the 1 over n to the n. And that's 1 over n over e. So this is the y-coordinate, and the question is, well, so I guess y is 1 over ne. And what do we want to show? We want to show that y is actually equal to ln of x over e. So let's calculate ln of x over e. Well, that's ln of e to the 1 over n over e. That is 1 over n over e. That is 1 over ne. Which is precisely y. So in other words, the y-coordinate of the maximum, it's ln of the x-coordinate over e, which means that xy is on that graph of equation y equals x over ln of x over e. And this illustrates another property of the French school system, because it turns out so in calculus, they actually learn more. In America, you learn more calculus than in France. But what I like is, with the French school system, it's like you're dealing more with unfamiliar math situations. Because, you know, usually in calculus classes, you know what technique to use, and there's just one technique you can use. But here, it's slightly kind of confusing because you have ends going on, and sometimes it's not quite clear what you have to use. So that's why I like this too. But again, no, not to talk badly about the American system. I love the college system. I think it's better than the French university system. But I also like this part of the French high school system. And also, another thing that's kind of cool is, even though you learn less calculus than in America, you learn a bit more of other topics. Like you do a bit more of combinatorics and probability, or even complex numbers, or stuff like parametric equations and stuff. So it's very neat. And you also learn how to write a couple of proofs, like by induction or by contradiction and all those things. Alright, so that was one thing. So that was the second part of the story. And since we talked derivatives, let's also talk integrals. So let's now show the following. Show that our functions are kind of squeezed between 0 and ln of 5 over x to the n on 1, 5. I'm not saying those questions are too difficult. I just really want to illustrate kind of the differences. They are certainly harder questions, but this one I like. It's kind of standard because lots of people know calculus. So how do we do this? Well, let's start on the interval 1, 5. We know that ln of x is increasing. So it's between ln of 1 and ln of 5. So if 1x is between 1 and 5, and you would write because ln is increasing on the interval 1, 5. And then how do you go from this step to this step? You just divide by x to the n. So x to the n over x to the n and x to the n, which is legit because x is positive. And finally, ln of 1, that's just 0. So ln of 1 is 0, and then this just becomes 0. So indeed, our function is squeezed between 0 and ln of 5 over x to the n. That's one thing. Then next question is, and again, if you've taken calculus, you will laugh about this, but I think it's important because otherwise it's not, you can't do C. So now let's show that the integral from 1 to 5 of 1 over x to the n dx is 1 over n minus 1, 1 minus 1 over 5 to the n minus 1. So I did say that the questions depend on the other ones, but kind of in order not to be unfair, sometimes it do tell you the answer to one question so that you can tackle the other one. Now, how do you do this? Just standard antiderivatives. So this is the integral from 1 to 5 of x to the minus n dx. And then you just add 1 to the exponent, minus 1 to the n over minus 1, minus n plus 1. And then from 1 to 5, and that becomes 5. So 1 over minus n plus, so 1 minus n if you want, over, so 5 to the minus n plus 1 minus 1 to the minus n plus 1. And that becomes 1 over 1 minus n over, if you want, 1 over 5 to the n minus 1 minus 1. And then, well, to get from 1 over 1 minus n to 1 over n minus 1, you do minus. So this just becomes minus 1 over n minus 1, 1 over 5 to the n minus 1, minus 1. And that becomes 1 over n minus 1, 1 minus 1 over 5 to the n minus 1. That's precisely what we have here. So that's good. And lastly, again, as I said, those questions depend on each other. So first of all, we showed that this is squeezed between 0 and this. This integral kind of to the right is this. And then lastly, well, you might see it's a kind of setup for the squeeze theorem. So let's actually show that the area under the functions fn, they converge to 0. So let beautiful an be the area of region between x equals 1, x equals 5, y equals 0, and our curve. So if you want, just as a picture, this is 1, 5, and as I said, this is sort of our graph, Cn, and we want this area here, ln of x over x to the n. And let's show, not as x goes to infinity, but as n goes to infinity, show an goes to 0 as n goes to infinity. And again, this is question C, so we probably have to use the other questions. Well, first of all, let's use this. We know that this is true by A, and then the nice thing about integrals is that we can just integrate an inequality. So if you integrate this from 1 to 5 dx, you get this, 1 to 5 dx, and this from 1 to 5 dx. And then, well, the left-hand side is 0. The right-hand side, the middle is what we want. And by the way, I know, if you're taking calculus, you would be like, oh, why don't you just use a substitution rule? They haven't learned the substitution rule in that course. So they just do until integration by parts. And again, you might laugh at them, but don't laugh, because this is a great question in showing how to do a math problem if you don't know all your information. And it might seem silly in calculus, but this is very important for upper division math if you don't know what to do. because kind of the problem in calculus is they teach you a bit too much. They don't really teach people how to like think in unfamiliar situations. But what I like is in the French school system, they do. And so then, that's less or equal, this is a constant, so this constant comes out. The integral from 1 to 5, 1 over x to the n dx. And this we have calculated in a previous problem, in part B. So that's ln of 5 times 1 over n minus 1 times 1 minus 1 over 5 to the n minus 1. And then the rest is just a squeeze theorem exercise. So why is that? Because you see, this is like the x disappears because we integrated, and n, so the point is this number would just depend on n. So this is a sequence, which you also learn a lot in the French school system. So this whole section on sequences. So this is an, this, let's say, small an, and this is small bn. So we know area is squeezed between two sequences, but limit n goes to infinity of an, that's the limit as n goes to infinity of 0, which is 0, and the limit as n goes to infinity of bn, as n goes to infinity of ln of 5 over n minus 1 of 1 minus 1 over 5 to the n minus 1, and that is 0 times 1. And 0 times 1, you think it's an indeterminate form, but it's not. 0 times 1 is 0. And so, though our, our area, it's squeezed between basically 0 and 0, so by the squeeze theorem, the limit as n goes to infinity of our area is 0. And I know you can use this U-sub, but I think this is a clever way that illustrates the squeeze theorem. So I hope now you had this exotic taste of a French math final exam. So if you want to see more math, please make sure to subscribe to my channel. Thank you very much.